All right, so today we'll talk about currents. Okay, electric currents is what we're talking about. So, for instance, a breeze is a mass of air flowing. That's a material current. So, electric currents is what we're going to talk about. And here's the deal. Okay, that's my son helping myself. All right, let's say you have a hunk of metal and you throw a bunch of charges on it. So let's throw a bunch of negative charges, electrons on it. What happens?
The exterior surface gets charged.
I'm sorry?
The exterior surface becomes charged.
Yeah, so it's a metal. The charges will distribute on the surface. And what is the thing that is driving their distribution? How do they distribute?
They distribute evenly around the surface.
They distribute such that the electric field everywhere inside is zero. That's what drives. Huh? All right, so in a static situation, the electric field inside a metal is always zero. All right, now we'll take this piece of metal. So in a static situation, it's the electric field inside is zero. By the way, do you guys remember this is a equipotential surface? Which way is the electric field pointing?
The one with the lower voltage.
All right, right. So there'll be an electric field pointing this way. Okay? All right, let's connect a 12-volt battery to this piece of metal. All right. So we'll keep it simple. It's 12 volts here, 0 volts here. Whenever there's a potential difference, there'll be an electric field. So here's a way to establish an electric field inside a metal. Connect a battery to it. Yeah. And by the way, so if you double the voltage, if you connect a 24-volt battery, this electric field will double. Okay. Now, if you have an electric field in a metal, what is a metal? It has a bunch of free electrons. Okay. These electrons will respond and move in the opposite direction. Yep. So as long as a battery is connected, you'll have charges moving. And this is the electric current we're going to talk about in this chapter. Yep. The instant you disconnect the battery, what happens?
They stop moving.
They go to the surface.
Oh,
They become a surface. It becomes a.
well, so it was neutral. They were evenly distributed.
Yeah.
The instant you disconnect the battery, the electric field goes to zero, and the motion of the charges stop. All right? All right. So we'll talk about a bunch of this stuff, drift speed and so on. Okay. All right, so here's what you observe macroscopically. We want to understand it at a microscopic level too, but so I gave you a picture sort of at the microscopic level. So here's a battery, here's a piece of metal, again, the tungsten wire inside, and that has the property that how does light work?
The tungsten wire resists the electric current, creates heat and light.
Right, so when the electrons bump into the tungsten atoms, they excite the tungsten atoms, which when they de-excite, they'll emit light. Okay. Anyway, you close the switch and the current flows and the bulb glows. Okay. What is this? This is a positive terminal, so the current is flowing in this direction. By the way, so when a current flows, it's actually electrons that flow in that direction. So we had adopted this direction of current before we knew about electrons. Okay. So that's the convention. Okay. And when you connect the battery this way, the current flows this way. You see the bulb doesn't care which way the current flows, it glows equally bright. Okay, so it doesn't care about the direction of the current. What happened here?
You have two in a series.
Yeah, you have two in a series, and look, they're not glowing as bright.
The
Okay.
voltage is essentially split between the two of them.
What happened is, okay, the resistance has doubled, the current has halved. So the current here is I by 2, R, okay? And the power dissipated is, okay, well, so the power is, you will learn in a second, power delivered is V times I, or I square R, okay? So each bulb, the resistance is the same, the current is halved, so this thing is glowing 1/4 times as bright as that. Okay. What happened here?
Voltage doubled.
Voltage doubled, the current doubled. This guy is glowing 4 times as bright as that. Okay. So this will run down the battery in half the time of this, right? Here they're connected in parallel, the current is the same, these guys are glowing as bright as that. Okay. Anyway. All right, so here's a hunk of metal. Here are the, you guys remember? So here's, let's say this is copper or whatever. Each copper atom, let's say on the average, lets go of 2 of its outermost electrons, so it's doubly charged. Why does this happen?
Because it's easier for it to drop its outer subshell.
Because this is the lowest energy configuration. Okay? So it happens this way. All right. Now, you can think of these electrons as like the gas in this room. So we talk about it as a free electron gas. Yeah? And these electrons are moving about like crazy. And on the average, they're going at about 1,000 kilometers a second. That's from here to DC. That's how fast they're moving. And they're colliding with those positive ions and stuff like that. You can think of it that way. But they're not going anywhere on the average. You paint an electron red, and the probability is fairly high that you come back 3 days later, it's still here in this location. Okay? So on their average position, so there's no net flow of electrons. Now, connect a battery to it. What does the battery do? It establishes an electric field. And so, on top of that random motion, these electrons acquire a drift velocity. So now, on the average, they're moving to the left. Okay. And the drift velocity is about 1 millimeter a second. Okay, so did you guys understand this? I mean, on top of this 1,000 kilometers a second from here to DC a second, on top of that random motion, there's this 1 millimeter a second motion. And that is part of the current. That's the current. Okay, so that's what's going on. Okay. So when electrons move through conductors, the speed between collisions is of the order of 10 to the 6 meters per second. 10 to the 3 meters is a kilometer, so 1,000 kilometers a second. In the absence of an electric field, no net flow of electron occurs. Typical value for time between collisions is 10 to the minus 14 seconds. So an electron will hit atom in 10 to the minus 14 seconds. So time between collisions is that. And mean free path, the distance between collisions is about 10 to the minus 8 meters. You guys remember the size of an atom?
10 to the negative 15.
10.
That was from
That's the nucleus. 10 to the negative 10. So they go about 100 atoms before they collide with an atom. Yeah. So when a conductor is connected to a battery, before I do that, here's a piece of wood. I connect a 12-volt battery to it. What happens?
Nothing.
Yeah. So there is an electric field established there, except that there are no free charges to respond to the electric field. Okay. So when a conductor is connected to battery, it sets up an electric field inside the conductor, which causes a current to flow. Because a conductor has free charges, those free charges will respond to that electric field. Okay. So the drift speed is the average speed of the electron in the presence of an electric field is called the drift speed. Okay. So you establish an electric field in this direction, the electrons will drift in that direction. Okay. So drift speeds are of the order of 10 to the minus 3 meters is a millimeter. So it's about a millimeter a second. You know? So So, you know, all puzzles are posed in a misleading way, right? All right, so I'll do the same thing. So here's the circuit. There's the switch on the wall. We just learned that electrons, the drift speed is, what is the drift speed?
2 times 10 to the minus 4
Yeah,
meters per second.
so a millimeter a second roughly. I'm going to close the switch. This is a light bulb. I'm closing the switch, that's about 20 meters away, but it still comes on immediately. What's going on?
The electrons themselves are traveling slowly, but the collisions are so fast, it's kind of like a Newton's cradle, how it just immediately knocks the furthest one down.
No, it's colliding with the stationary ions. They're not colliding with other electrons.
The free electrons in the wire start to move when you close the switch, because the electric field gets created instantly, right?
There you go. So the moment you close, the electric field gets established at the speed of light. Soon as the electric field is established here, these electrons respond immediately. Okay. All right, so to make sure we understand this, let's imagine that again, this battery is on Earth, the switch is on Earth, this is the sun. So every morning when you close this switch, that's when the sun starts glowing. Okay. So will the sun start glowing immediately? You close the switch?
It takes 7 minutes.
8 minutes. Yeah. Okay. So it takes 8 minutes for the electric field to turn on there. Okay. Even at the speed of light. All right. So we understand drift speeds now. Okay. So now we'll define electric currents. You guys are all aware of electric currents. So here's a wire. We're going to stand here And the current is how much charge is passing you by per second. Okay, so the electric current denoted by I is the rate of flow of charge. Okay. And the unit for currents is ampere after Mr. Ampere. And you have a current of 1 ampere when 1 coulomb flows by in every second. Okay. So for instance, when you start your car, when you crank your motor, you need electric large current, 200 amps. Okay. And again, to give you a sense, a large thundercloud has only about 50 coulombs. Okay. So if 50 coulombs passed by in 1 second, that's only 50 amps. All right, here are some of the currents we encounter. In a lightning, you'll have 10,000 amps of current flowing. In the auroras, you have 1,000,000 amps of current. A light bulb is about 1 amp. Here's a 10 amp fuse. In your telephone, you're using milliamp currents. Okay. When your neurons fire, it's a nanoamp current. Okay, and so okay, when you take a piece of metal, it's electrons that are carrying the current. Okay, the electrons are the free ones. The positive charges are anchored, and so these are carrying currents. In semiconductors, you guys have heard of holes? Have you guys heard of holes in semiconductors?
In terms of the valence shell of atoms, if they have a spot to receive more.
Yeah, very good. Yeah, okay. So, so here's I'll give you a different analogy. So let's say you've seen the Mancala game. Okay. So let's say there's an empty spot here. No, there's an empty spot. There's an empty spot here. This is filled with marbles. And what we'll do is we'll move the marble here. Now this became the empty spot. We'll move the marble here. This became the empty spot. So it's the empty spot moving in this direction. That's called a hole. And this empty spot behaves like a positive charge. So that's what's happening in semiconductors. Here's the band structure. Okay, so this is the valence shell. So if there are a few empty, the conduction band is, it doesn't have any electrons. Here are a few empty levels, so the electrons fill that, and the empty spots travel to the right. Those are the holes. Okay, so they're acting like positive charges. Okay. Of course, in a electrolyte, so you take a salt solution and pass a current through that solution. Chlorine atoms will flow like that. Sodium ions will flow like that. So there are both positive and negative charges. Okay. So in metals, you have negative charges carry the current. In electrolytes, you can have that. In semiconductors, you could have just holes carrying currents and so on. Yeah. All right. Most of the time, we'll just be talking about conductors. Okay. All right. So here's a piece of copper, or whatever, and it's carrying a current I. Okay. So this current I is N is the number of free electrons per meter cube. That's the number of free charges. And what do we mean by free charges? The charges that can move. See, the copper atom has plenty of electrons. It probably only lets go of 2 of its electrons to move about freely. How many electrons does copper have? 29. So 27 of them it's holding on to, they're going nowhere. I guess so. the free electrons. So how many free electrons there are per unit volume? Okay, here is a meter cube. This is a meter cube. In a good metal, there's about 10 to the 28 free electrons per meter cube. So that number is huge. Okay, that's 10,000 moles. That's the charge of the carrier. Okay, so what is this?
Drift speed,
Yeah, and that's how much?
like 10 to the negative 4 meters per second.
Yeah, so about a millimeter a second, and this is the area of cross-section of the wire. All right, so here's something I want you to sort of understand and remember. Here's a wire. And I've connected a 12-volt battery, and there is a current flowing in this thing. So there's that current. Okay? Now what I'm going to do is I'm going to double the voltage of the battery. I'm going to connect a 24-volt battery. What happens to the current? Doubles. Okay. The current doubles. Let's see, what changed? Did this change? Did this change? Q changed? That's the charge of the electron. That didn't change.
Oh, yeah, okay.
Did A, the area of cross-section, change?
That must be the drift.
Yeah, so you double the drift velocity. Okay? So when you double the voltage, what happened was you doubled the electric field inside the wire, which doubled the drift velocity. Okay? All right, we'll talk about current density. So this is the current through this wire. Current density is just the current per unit area. You divide the current divided by the area of cross-section, and we define the current density. The reason we define the current density is because the current density is what is proportional to the electric field. Okay? So remember, you established an electric field inside the conductor, and the current density is what's proportional. Okay. So Mr. Ohm discovered this, and he discovered that the current density is proportional to the electric field. Now, so this is Ohm's law, of course, but if you go to a store and buy instruments to measure stuff, you don't measure this. What you measure is the current. You don't measure this, but you measure voltage using a voltmeter. So what we're going to do is we're going to reformulate this into quantities that can be easily measured. You can't easily measure electric field inside a conductor. You can't measure the current density and so on. Okay, this is called the conductivity of the material. And as the name suggests, this number for copper and wood, which one would it be higher for? Copper. And it's probably billions of times higher for copper than wood. Okay? This is called the resistivity. So if it's a good conductor, it has low resistivity. Okay? All right, so now we're going to reformulate Ohm's law into a form where the quantities are easily measured. Okay, so the voltage across a wire is the electric field times the length of the wire. Okay. Now voltage differences can be easily measured. Okay. And so E was J over sigma, and so E times L is JL over sigma, and J is so voltage is E over E times L equal to J over sigma times L. J, the current density is I over A. So this is equal to I L over. Yeah. And this quantity is called the resistance of the wire. Okay. So the resistance of the wire is inversely proportional to the conductivity. Higher the conductivity, lower the resistance of the wire. So the resistance of a wire depends on the length of the wire, is inversely proportional to the area of cross section, and inversely proportional to the conductivity. And conductivity is inverse of resistivity. Okay, so the resistance of a wire is the resistivity of the wire, of the material, times the length of the wire divided by the area of cross section. So thicker the wire, smaller the resistance. Longer the wire, more the resistance. Okay? So here is a form of Ohm's law that is used in everyday life because voltages are easy to measure and currents are easy to measure. So what this says is voltage and current are proportional to each other. You double the voltage, the current in the wire doubles. Okay? So the resistance of a wire is the length of the wire divided by conductivity divided by the area of cross section, or resistivity times the length of the wire divided by the area of cross section. Okay, so here's resistivity for conductors. See, for resistivity for conductors is very low. And resistivity for glass, look at this, is 10 to the, we'll say 10 to the 12. That's 10 to the 20 times greater. Okay, what that means is the following. What these numbers means is the following. Okay, so you take a wire and connect it to a silver wire, and let's say this is 10 volts and 1 amp current is flowing through there. And instead, if you replace the silver wire with the glass wire, the current now will be 10 to the minus 20 amps. Okay? So that's what those numbers mean. Hard rubber, again, 10 to the minus 20 amps. So that's why you wear rubber-soled boots. Okay? You catch a live wire, you know. If you're wearing a conductive boot, then your body has low resistance, current will flow through here. And that current flowing through here might stop your heart. Now, if you have a rubber boot, you got a large resistance, and the current won't go through here, it will find some other way to go. All right, so here's a simple circuit. Okay. Remember we said if you have a voltage difference, there will be an electric field between them. Okay? So here is the voltage on this circuit. The wires have essentially no resistance, so there's no voltage drop across there at all. Okay? There's a voltage drop there, and then and across the resistance all the voltage falls. And so there's an electric field there. Okay? And electric field there as well, but anyway, so this is the voltage. You guys remember the potential energy of a charge is charge times the voltage. So think of a positive charge. So this positive charge has potential energy here, and then when it falls down there, it's lost all its potential energy. What happened to that energy? Huh?
Converted either into heat or
Right.
kinetic energy.
Yeah, so whatever this load was doing, if it was a washing machine, it got converted to kinetic energy. If it was a heater, it got converted to heat. It was a bulb, you know. Yeah, so that electrical energy got converted to other forms of energy here in this device. Okay, now it's lost all its energy. What do you do now? Now the battery takes its chemical energy and converts that back to potential energy, electrical potential energy, brings that charge there. How long can you do that?
So the battery runs out of charge.
Till battery runs out of chemical energy. All right, so that's what's happening. Okay, so when you go buy a battery, what is it that you're buying?
Chemical energy.
Yeah, you're just buying a store of energy. All right, these are resistors, and these bands mark the value of the resistors. Okay, so this color code is for the value of the resistance. Okay, uh, so this tells you the accuracy of the value. The first band is the first number, the second band is the second number, and this is the power of 10. So this is how this is read. Brown is 1, green is 5, and again brown is 1. So times 10 to the power 1. Okay, the third digit gives you the power of 10. Okay, so this is 150 ohms. That's what this is telling you. This resistor is 150 ohms. Okay. Okay, help me out with this one. I see that as red.
Yeah, it is red.
Okay. So red is 2, black is 0, 200 ohms. Okay. This is a capacitor. This is a transistor, it looks like. I don't know what this thing is. Anybody know what this is? All right. So resistors, those bands tell you the value of the resistance. The value of the resistance is indicated by 4 color bands on the plastic capsule. The fourth is a tolerance for the range of values. Okay. So that tells you the accuracy. Gold is 5% accurate, silver is 10% accurate, colorless is 20% accurate. Yeah. All right, so in the circuit, what is happening? You went to the store and bought a battery. You bought a store of chemical energy. And here you had this device. This is the load. Okay, what is your device? It could be a toaster, it could be a bulb, it could be a washing machine, or whatnot. All right, this delivers energy to this device, and this device, what is it? It's an energy converter. It converts into whatever it is that you want to convert. Yep. Okay, so the rate at which energy is delivered to this device, that's power. Okay. So if V is the terminal voltage, this is the rate at which this guy is delivering power, and that's going to that thing. You know? So the rate at which power is delivered to the load is V times I. V is the voltage across times the I, or I square R. I is the current flowing through the device, R is the resistance of the device, or V squared over R. Okay. So the rate at which battery delivers energy to the resistor is given by that. Energy delivered by the source to the load is converted to heat, light, etc. Okay. All right. So our model right now is, I mean, all you guys probably will have solar panels on your roofs eventually, but anyway. So the model we have set up is we have some large power plants, and then power is delivered long distance to various homes and stuff like that. Okay. Now, if you put copper wires, that would be too expensive. These are thousands of miles, so you use cheap material for transmission lines. They have high resistance. Okay? So this is the power that's being delivered by Hoover Dam. Okay? This is the power that's being delivered by Hoover Dam. And here is its I square R. This is the resistance of the transmission, and this is the resistance of the load. So that could be, the load could be a city. That's the city, let's say. So here is Hoover Dam, this is the transmission line, and this is Daytona Beach. Okay. How much power is lost in the transmission line? This much power is lost in the transmission line. Power in the transmission line. Okay, so it's like you're transporting gasoline in a leaky tanker. Okay, what can you do to minimize this loss?
Reduce resistance.
You can, well,
Jack up the voltage.
yeah, so you see, well, the resistance is, that was decided by how much money you were going to spend on the wire. So that's fixed. The only thing you can do is, let's say you reduce the current, then you can reduce the transmission loss.
Then you'll lower the total power to the load.
There you go, okay? So, how do you fix that? So you see, this is the power delivered by Hoover Dam, okay? If you choose to deliver the power at high voltage and low current, then you can minimize that. So that's what happens. You have a power plant, it produces power at, let's say, 10,000 volts. You jack it up to 8,500 volts to reduce the current. And then you reduce the transmission losses. And then you don't want 850,000 volts coming to your house. Then you jack it down to 240 volts. Okay, so that's where you use the step up and step down transformers. Yeah. The power loss in the US is about 6%. Transmission loss.
That seems pretty good.
Hmm?
That seems pretty good.
Well,
Better than a car.
with that?
It's better than a car.
Oh, yeah. Yeah, but you want to minimize that because 6% of $1 trillion is $60 billion. Yeah. All right. There are devices. So this is a diode. And the property of this guy is it only lets current this way. It doesn't let current this way. So it's like a gate. Okay, it's a one-way gate. And all right, so essentially, so the way the diode works is if this end is about 0.7 volts above this end, its resistance goes to 0, it essentially becomes an open gate and current flows this way. Okay, if it's less than 0.7 volts, then it doesn't let through current. Okay, so if this was 0.1 volts and 0 volts, it's not an open gate anymore. And of course, if it's negative voltage, then it won't let any current at all. So the diode is a one-way gate essentially. Okay, so here is the voltage response of a diode. You see, negative volts, it doesn't let any current. This is current and this is voltage. Okay, so current and voltage. So what we're doing is, what we're talking about is the following. We are plotting this current versus the voltage at this point. Okay, when the voltage at that point is minus 1 volts compared to that, the current is 0. And up to 0.5 volts, the current is essentially 0. And at 0.7 volts, when this becomes 0.7 volts and this is 0 volts, essentially this becomes an open gate and the current flows. Okay. On the other hand, you take a resistor, a plain copper wire, And if you apply minus 1 volt, the current is flowing in that direction, and you apply plus 1 volt, it's flowing in that direction. And the response is linear. You double the voltage, the current doubles. Okay? So if you have a current versus voltage, if the response is linear, these materials are called ohmic materials. Okay? They obey this law. They obey Ohm's law. You double the voltage, the current doubles. If the current versus voltage of a device is non-linear, it's called a non-ohmic device. That's all. Do you guys know how does a thermometer work?
Mercury expands as
Huh?
the mercury changes volume proportional to temperature.
Yeah. So what is happening is, as you heat up mercury, oops. No. So you have a bulb of mercury, and when you heat up the mercury, its volume expands. Does the volume of mercury increase by a large amount? No. So what do you do? How do you measure the increase in volume?
You give it only one path to go.
You give it a very narrow path to go. Okay? So even small increases in volume will show up there. Okay? But, so what was the proxy for temperature? Volume of mercury was the proxy for temperature. So that's how all thermometers work. You need some physical property that's a proxy for the temperature. Okay? Here's a material whose resistance changes quite a bit with temperature. Okay? So its resistance, so as its temperature increases, the resistance is decreasing. What is happening?
More electrons are being.
Very good. The number of charge carriers are increasing. Yep. So how do we measure the temperature? Well, what we do is we use a thermistor, okay, and connect it to a 10-volt battery, okay, and as the resistance decreases, as the temperature rises, resistance decreases, and current in this thing will increase. So current is the proxy for temperature. Okay.
Use those in engines?
What's that?
Use those in engines to check engine.
Thermocouples.
No, thermocouples generate electricity when you heat them. This is in the old times. They had these strip thermometers. That's what was happening.
Is this how those like instant read thermometers work? You've seen those, no.
How do you use them instantly?
You like stick it in a piece of meat and it will like tell you
Oh,
the temperature?
no,
Or is
those
that
are the
just a-
those are thermocouples.
Those are thermocouple,
Yeah.
okay.
So I can't remember. I do remember strip thermometers.
I don't know what that is.
Hmm?
I don't know what that is.
Yeah, you just stick a piece of thing to your
Oh, that's why you're.
yeah forehead. But nowadays these things are cheap enough. Yeah. So anyway, what you want to do is find a property that varies quite a bit with temperature, and also if you want to use for human things, you want that response in this range of temperature. You might have a physical property changing in various regions of temperature scales, and so it'll be a good thermometer in that temperature scale. You know. So for instance, a copper wire would not make a good thermometer. Okay, its resistance is not changing enough. Okay, see, its resistance is, for a 100-degree rise, its resistance is changing only about 20%. Okay, and the current would change about 20%, so that's not good. For this guy, you see, it's changing for a 100-degree change, the resistance is changing 400%. That's a good thermometer. Yeah, so for most metals, the resistance varies linearly with temperature. Alpha is called the coefficient of temperature coefficient. Okay, so what is it called? Okay, it's some coefficient. Okay, but it varies linearly. Okay, what this graph shows you is, okay, so here's for most of the temperature range, the resistance varies linearly. But when you come very close to absolute zero, now there's a residual resistance. So at 0 degrees, there's a residual resistance for most metals. And that's because of the impurities and stuff like that, or defects. For semiconductors, the resistivity increases. Why?
Because there's less free moving charges.
Very good. So you're decreasing the number of charge carriers. There are some materials, you reduce the temperature, and the resistivity seems to go to 0. What does that mean?
It means you could run a ton of current through it without losing a ton of energy.
Without, so here's a wire. You decrease the temperature of the wire, make it superconducting, you get the current going, and then you can remove the battery, and the current will keep flowing. It's like a hockey puck, air hockey puck. You get it going, the resistance is 0, it'll move forever.
But wouldn't the heat generated cause it to come above 0?
So how is the heat generated?
Resistance.
Hmm?
The I squared R losses.
I'm sorry?
The
How's the heat generated in the copper wire?
collision of electrons with
The ions.
the ions.
So if you're not generating any heat, you're not colliding with any ions.
I don't understand.
So you're missing every ion. You're going through the copper wire.
Oh. Okay. Never mind.
So they've done experiments like this. You start a current in a ring, and the ring current hasn't decayed for 10 years. Okay.
Useful.
Huh?
It's pretty useful.
Yeah. So
Can you do anything with it?
yeah, you can do stuff with it. Okay.
As soon as it is put under load, it's over, right?
All right. So here's what you could do with it. So in the next chapter, you'll learn if you have a current like this, it behaves like a magnet. Okay. So here's the rule. Here's the direction of the current. That's the direction of the magnet. That's the North Pole, that's the South Pole. Put a superconductor in a train and put magnets on the track. Now you have a train that's floating. This is a maglev train, and you push it to DC and you haven't used any gas. Yeah. So, all MRI machines use superconducting magnets. Yeah. So nowadays, so there's a wire which is superconducting, and you're passing a current which is producing this magnetic field. When you put the patient in this, so what you need is a strong magnetic field. So MRI machines have 1.5 Tesla, 3 Tesla, and I've seen pictures of 7 Tesla. The stronger the magnetic field, the better the resolution of your image, and the more expensive the MRI. So you've done a 3 Tesla one? Huh?
I wish.
Okay. Well, anyway, so
The field is still pulling the load, right? It's not completely free. They still have to cool the magnets. They still have to
Yeah, you're cooling
add
the
load
magnet.
to the field. And obviously, it's much cheaper than doing the other way, at least for electricity.
Yeah, you're not wasting any heat.
Yeah.
So when that electron collides with the ion, it's losing all its energy, which gets converted to heat. So the electrical energy was being converted to heat, which you didn't want. Yeah. All right, so there are certain materials whose resistivity will go to 0 below a temperature which is called the critical temperature. Superconductivity was first discovered in mercury in 1911. And it became superconducting below 4.2 degree kelvins. That's very cold. So ever since then, the search has been on for a higher and higher TC. The holy grail being you want something to be superconducting at room temperature. Right? You understand? Yeah. But, so here's another thing. So to get to that temperature, you need liquid helium. Liquid helium is $2 a liter. And not only that, helium is a limited supply. You release helium into the atmosphere, what will happen?
Float away.
It'll go into space. Okay? So if you're using helium, it needs to be in a closed cycle. Liquid nitrogen is 10 cents a liter. The other advantage is, you don't have to use it in a closed cycle. Okay? So liquid nitrogen is cheap. And nitrogen becomes liquid at 77 degree Kelvin. So even if you get TC about 77 degrees Kelvin, you suddenly opened up a lot of applications. Right? It's become cheaper, superconductors. All right, so the search was on for higher and higher TC since then. And here, look at this graph. Till 1985, we got nowhere. In 85, suddenly the floodgates opened. Yeah. These are all ceramic materials. Nobody ever thought of using those. But then the floodgates opened. And I don't know what the critical temperature is now, but anyway, see, this is 150 degrees Kelvin, the critical temperature. And now the problem with some of these materials is you can't make them into wires, nice wires and stuff. Okay.
Says the highest critical temperature achieved is 250 Kelvin from a lanthanum hydride under a high pressure found in 2019.
Mm-hmm. So, okay. So again, high pressure, that puts restrictions on applications and stuff like
It's like 200 gigapascals.
that.
High pressure.
So this is a good one to watch.
Jellyfish Lighting is an all-in-one permanent exterior lighting system. Through an app on your phone, you are able to decorate.
One doesn't have to be a passionate fan of model trains to be fascinated by the way this steam engine looks. Hovering a few millimeters over the rails, it goes round and round without any friction and without any motor. On top of that, it really steams. But it's not water that evaporates inside the model steam engine, but liquid nitrogen, so cold that humidity condenses on it. The core of this magnetic levitation train is a superconducting material which conducts electric current without any resistance at temperatures below minus 183 degrees Celsius. In this state, it's able to trap magnetic fields. The resulting magnetic forces cause not only the levitation, but precision control above the rail, which is made of conventional magnetic material. An impressive experiment is designed to demonstrate how strong the forces are which hold the superconductor on the track. The superconductor is brought into a certain distance of a few millimeters above the magnetic rail and cooled down in this position using liquid nitrogen. Reaching the specific transition temperature of minus 183 degrees Celsius, the superconductor traps the magnetic flux of the outer field. Now we can remove the shim of a certain thickness which determines the distance. The superconductor has now memorized its position within the field of the rail. The superconductor is fixed at this distance and can only move along the magnetic rail even when turning upside down. But the effect lasts only as long as the superconducting state in the material is maintained. To set the superconducting levitation train in motion, one has only to give it an initial impulse by hand. Due to the lack of friction, the steam engine goes round and round until the liquid nitrogen is evaporated and the material warms up. Then the effect of superconductivity ceases, and what has been a strong magnet at low temperatures turns into a ceramic material without particular magnetic properties. Above the so-called transition temperature, superconductors are no longer affected by magnetic fields, and the locomotive drops back to the rail due to the effects of gravity.
So you can go back and go to the physics department and have John Marco show that to you. Do you know who John Marco is?
Yeah.
Okay.
Fancy t-shirt guy.
Huh?
Fancy t-shirt guy.
He's fancy t-shirts?
Yeah.
He wears fancy t-shirts?
Fancy is the way to put it.